This video will cover section 5.1 using fundamental identities. The objectives will be to recognize and write the fundamental trigonometric identities. We will cover those in a minute or review them. And then we will use the fundamental trigonometric identities. And those are the ones that we discuss. I'm not sure, perhaps section 4.3 or 4.4. Those include the quotient identities, the reciprocal identities, and the Pythagorean identities. So we will use the fundamental ones to evaluate trigonometric functions, to simplify them. This is so important in trigonometry because we could go from a very complex trigonometric expression to a very simple one, and they are a lot easier to evaluate. So this is going to be a very useful skill that will carry across not only this course but also your calculus. And perhaps if you go into engineering, you will see a lot of these things again. Well, to simplify the expressions and also to rewrite them. And like I said, when we simplify them and rewrite them, it's easier to manipulate them. Okay, so how are we going to do this? We're going to evaluate trigonometric functions. We're going to simplify trigonometric functions and develop some additional ones that are going to be derived from the fundamental ones. So the additional ones will come from the fundamental trigonometric identity. So we're going to extend our list. And then, of course, this will also help us to solve trigonometric equations. In this chapter, we're going to do more of that, of simple manipulating the identities and then use them to our convenience to use to solve trigonometric equations. So we have here the fundamental trigonometric identities. You might recognize them. So we have the reciprocal identities, and that will be sine and cosecant. They're reciprocals of each other. Also cosine and secant, and also tangent and cotangent. Those three are reciprocal. Then we have the two quotient identities, and first we have tangent is equal to sine over cosine. We also have cotangent is also cosine over sine. And of course, you could also see that from the fact that these two, tangent and cotangent, are reciprocals of each other as well. So it makes sense that sine and cosine are inverted. Then we went over the Pythagorean identities. And so the first one starts here. Sine square of u plus cosine square of u equals 1. That identity is going to be a lifesaver when we are trying to simplify things. And also on the next section, we will be exploring more about identities. So from that one, on a previous section, we derive two variations of it, and that was by us dividing by, for example, on the first one, let's see, to get this one here, we divided by cosine square everything, and then to get the second one here, or the third one I should say, of the Pythagorean identities, we divided the original by sine square all across, and that's how we arrived to it. Then in a previous section, we cover the co-function identities. Remember how angles that are complement of each other, or complementary to angles that are complementary, the sine will be, for example, my favorite angle or expression, sine of 30 degrees. The complement of sine is the complement of 30 degrees is 60 degrees. So the sine of 30 degrees is the same as the cosine of the complement of 30 degrees. So those are what we call the complements. Now, how could we find this in general terms? So if we were talking about sine of x, the complement complementary identity to it, it will be the cosine of the 90 degrees minus x. And so that's why and I'm kind of like talking about this one here, and that is why we have pi over 2, because remember 90 degrees is the same as pi over 2. So it makes sense that they are written that way. Okay, and of course, if we're talking about cofunction, sine and cosine go together. Like the sine of 30 is the same as the cosine of 60. And of course, based on that, you could also reverse it. Then we have here tangent goes with cotangent for complementary. So tangent and cotangent go together for reciprocal identities, but also for cofunction identities. Then we have secant goes with cosecant. And see, this is different from reciprocal, because for reciprocal, sine goes with cosecant. Sorry, sine goes with cosecant for reciprocal. But for cofunction, secant and cosecant are the ones that go together, just like sine and cosine. Okay, and then we have also discussed this once, the even and odd identities. And we did explain this back in the chapter 4. So we know that sine is a odd function. And because sine is odd, then also the reciprocal, which is cosecant, will be odd. Okay, and then we have that even will be cosine. And because tangent is the ratio of sine and cosine, we will end up with something that will be odd. And we did a demonstration of this in a previous section. So if tangent is odd, also cotangent will be odd. And that's how they go. And based on that, if they are even, they are symmetric with respect to the y-axis. And if they are odd, they are symmetric with respect to the origin. So those are things that we cover in previous sections as well. So we're going to use the Pythagorean identity. And we're going to use u. So sine square of u plus cosine square of u equals 1. And from here, we're going to derive some of those that were on the previous slide. And of course, we have that if we divide everything by sine square of u, everything. This one here will be a 1. Here, this one will give us, by using the quotient identity, it will be cotangent square of u. And here, by using the reciprocal identity, we will get cosecant square of u. Now, similarly, we have, if we start with the same Pythagorean identity, and now we divide everything by cosine square of u. And we could do that because we're doing it to both sides of the equation. So we're not really changing it. We're just changing the meaning. We're just changing the way it looks. So sine divided by cosine, it happens to be tangent. So tangent square of u plus this one equals to a 1. We say they cancel, but they don't disappear. They equal 1. And then finally, by the reciprocal identity, 1 over cosine square will be secant square of u. Okay, so now I call those our 3 Pythagorean identities, as you could also see from the previous slide. But now we could do more things with them. And so, for example, if we do have sine square of u plus cosine square of u equals 1, and you want to solve for sine square, then we will leave sine square where it is, sine square of u equals to 1, because we have a 1 on the right side. And then we could take the positive cosine square of u to the right side. So in this case, it will be negative, or you could think of it, you subtract it from both sides. And so that's another variation of it. So now let's do the same, but in this case, we want to solve for cosine square of u. So I'm going to start again by rewriting the original Pythagorean identity, and now I want to solve for cosine square. So cosine square of u is going to equal to 1 minus, because the sine square has an invisible positive sign in front of it, so minus sine square of u. Okay, so those could be very helpful as well, and they are just variations of the Pythagorean identity. Now, let's say that we want to find out what sine of u is. We don't want sine square of u, and so I'm going to pause the video for a second so I can write them down. So if I take, remember I was saying we want to solve for sine of u, not sine square. So how do we undo that square? We take the square root on both sides. And so that square root and the square of sine will cancel each other out. So that's why we have sine of u. And that will equal to the square root of the expression that we had before. Now, here, the plus minus indicates that your answer could be positive or negative. However, it will all depend, and I just realized that's not what I need. It will all depend on the choice of the angle u. And so you have to make a decision. Is that going to be in the first quadrant, second quadrant, third quadrant, fourth quadrant? Because remember that the signs are different. And so, for example, I'm going to write them in this order: sine, cosine, and tangent. So in quadrant 1, sine is positive because y's are positive. Now in quadrant 2 is positive. Quadrant 3, sine is negative. Then let's move on with cosine. So cosine is positive in quadrants 1 and 4, but it's because those are x values, and then they're negative in quadrants 3 and 4. And finally, for tangent, remember how tangent is the ratio of sine and cosine. So if you divide two positives, you will get, oops, sorry about that. You will get a positive, so tangent will be positive in quadrants 1 and also 3. Because if you divide two negatives, you get positive. And it will be negative in quadrants 2 and 4. Okay, so what I wanted to actually write was going to be coming from here, this equation here, which is a variation of the Pythagorean identity. So if we do have tangent square of u equals to, well, actually here we have tangent square of u plus 1. So I'm going to take the 1 to the right side, so it will be secant square of u, and then we take this plus 1 to the right, so it will be minus 1. Then what happened here is the square root was taken, so from there they cancel here, and that's what we have here, tangent of u, and then equals to the positive and or the negative square root of secant square of u minus 1. And this is only, you have to select the sign depending on the quadrant in which angle u will be located at. In example 1, we're going to be using identities to evaluate a function. One common application of trigonometric identities is to use given values of trigonometric functions to evaluate other trigonometric functions. So in this case, we are given the value, use the value of secant of u, which is equal to -3/2. And tangent in the fact that the tangent is positive. So first we need to figure out which quadrant we will be working with. So we're saying secant is negative, so that's the same as cosine, not the same, but the reciprocal of cosine. So in fact, to find the value of cosine, we will use, you could either do 1 divided, imagine a 1 over 1 divided by negative 3 halves, like that. And then this will turn into negative 2 over 3. Or you can simply look at the fraction and get the reciprocal of it by just interchanging the numerator and denominator. So it's negative 2/3. So where is the cosine negative? The cosine is negative whenever the x is negative. So that will occur here and here. Now they're telling us that the tangent, and in fact I want to use blue. The tangent is positive because it's greater than 0. So where is the tangent positive? In quadrants 1 and in quadrant 3. So where is where those two things happen? And that will be in quadrant 3. So that's where we are going to be working at, in quadrant 3. So if we have that the secant is negative 3 over 2, we already established that the cosine will be the reciprocal of it, so negative 2 over 3. Now, based on the definition of that, of cosine, this means adjacent over hypotenuse. And so we could say that negative 2, for example, is the x value. And then the hypotenuse is 3. Oops. So we are potentially working there. So this is going to be a negative 2. This is going to be a 3. So if we had a triangle of that form, and this is a negative 2, and this is a 3. I know if I move it as a triangle, it should be a positive 2, but I just don't want us to forget the fact that it's negative because we are in quadrant 3. And so the angle will be here. If we were using a reference angle, of course. And so to evaluate, we're not looking for the hypotenuse. So by the Pythagorean triangle, let's call this A. So a square, I'm going to go ahead and write the Pythagorean theorem. So c squared equals a square plus b squared. So if I want to solve for a square, that will be a squared is equal to c squared minus b squared. And if we want to solve for a by itself, that will be the square root of c squared minus b squared. And so that's what we're going to do to find what this value will equal to. So let's see. A will equal to the square root of c squared minus b squared. So that will be a squared is equal to 3 squared, that's c, or the hypotenuse, minus negative 2 squared. Now here I'm going to place the negative 2 in parentheses because you have to. In fact, if you don't do it, the calculator might not give you the correct answer. So anytime you square a number, whether it's positive or negative, you're going to get a positive solution. So 3 squared is 9. Minus, this minus comes from here. And now negative 2 squared is going to be positive 4. So now if we subtract these two numbers, we're going to get that a is equal to the square root of 5. And because we want to have exact solutions, we're just going to leave it as is. So this little number will be the square root of 5. Now, with that said, we could get any of the trigonometric ratios. And in fact, I just realized something. I need to correct myself. So this is what we were looking for. So that's where we should actually place a equals the square root of 5. I'm so sorry about that. The one that we were given was the actual adjacent side because remember, adjacent adjacent is going to be -2. And so if our angle is here, I'm just gonna erase this. Okay, let's just draw it again. Okay, so this was the adjacent side will be here. So -2. In fact, okay, -2 right there. So this will be our adjacent side. This is the adjacent side. And I had labeled it as the opposite. That's our triangle. And this is the one we were looking for. So that's going to be the square root of 5. In fact, it will be, we have to make a decision, and it's going to be positive square root of 5 if we're talking about triangles, but based on the Cartesian plane, it will be the negative square root of 5. And with that, we could get all the trigonometric values. And remember, just the angle is this angle here, like our reference angle that we will be using. Okay, so with that said, we could go ahead and answer the next one. So now, instead of looking, I could answer the question right away, that the sine of u, based on the Pythagorean theorem, and that we are in quadrant 3, it will be the opposite, which is the negative square root of 5, because we're in quadrant 3, divided by the hypotenuse. The hypotenuse, or the radius, if we were looking at a circle, it will always be positive. Remember that. So for the hypotenuse, that will be a 3. Now, if we were to solve this by using the Pythagorean identity, it would be almost the same. Well, it will be the same solution, but the steps, you know, it just depends on you. So we could have 1 minus, we're going to substitute the -2/3 that we had for cosine, -2/3, and we will square them because that's what we have here with the Pythagorean identity. Then to solve for sine square of u, let's go ahead and do the operation. So 1 minus -2 squared is going to be 4, and then 3 squared will be 9. When you square a fraction, you have to square both the numerator and the denominator. So then we're going to go ahead and subtract these two numbers. So 1 in terms of ninths, it will be 9/9. And if we subtract 4/9, then we're going to have 5/9. So now from here, remember, this is sine square of u equals 5/9. But we want to find sine, not sine square. So we take the square root. We could do that on both sides. And here this will cancel out. So we will have sine of u equals, and here we could say the square root of 5 divided by the square root of 9. And the square root of 5, because it is an irrational number, we will leave it like that. We don't want to approximate it. And then the square root of 9, it has an exact number. It's a perfect square. It's a 3. But remember that we were working in quadrant 3. And in quadrant 3, sine is negative. So we still need to consider that when we give our answer. And so there we have it. Sine is negative square root of 5. Now we're going to find the rest of them, and this will be pretty simple because we already know sine and cosine, and in fact we were given secant at the beginning of the problem. So secant was given to us, and that was -3/2, or you could also use the reciprocal of cosine. For cosecant, we're going to use the reciprocal of sine, and so we need to interchange numerator and denominator, so we could say -3 over the square root of 5. And then for tangent and cotangent, we're going to use For tangent, let's use the quotient identity. So that is sine over cosine. And we have those two values. So sine is negative square root of 5 over 3. And the cosine is negative 2 over 3. So if I multiply these two fractions, I will multiply the outer quantities. So that will be 3 times the square root of 5. Let's put the negative there in front. And then the inner numbers are 3 times negative 2. So let's see what happens here. 3 divided by 3 is equal to 1. We may say they cancel. So then we have the square root of 5 negative, because we still have this negative sign, divided by negative 2. And so 2 negatives divided gives us a positive. So this will be the square root of 5 over 2. And that is the answer for tangent. Now for cotangent, we could go ahead and just use the reciprocal of what tangent is. So we're going to take the reciprocal of this one, and it's going to be 2 divided by the square root of 5. However, we don't want to have irrational numbers on the denominator, so we're going to rationalize the denominator by multiplying by the square root of 5 top and bottom, because multiplying by this is like multiplying by number 1. So 2 times the square root of 5, and then on the bottom, square root of 5 times the square root of 5. We can look at it in many different ways. One of those is to think about 5 times 5, or 5 squared inside the square root. You cancel those, and then you will just have the 5, which is the purpose of rationalizing the denominator. Okay, and so those are all of your 6 trigonometric functions. For example 2, we're going to simplify a trigonometric expression, and that expression is given to us here. Sine x, cosine square x are multiplying each other. And then we have minus sine x. So what we're going to do is first, I wrote down the Pythagorean identity here. And what I did on the next step was to solve for the sine square of x for that one. So if I want to solve for it, I just had to move the positive cosine square x to the right side. So because it was adding on the left, is subtracting on the right. Now that looks almost like this expression here. The problem is that they have opposite signs. So if you notice, with the Pythagorean identity, cosine square is negative and the number 1 is positive, and the other one that I have here, it's the other way. So let me explain to you how I got that one. So from here, I factored out the sign, the factor that they have in common. So here we do have 2 expressions. This is one expression or one term, and this is another term. Why do I say they're 2? Because they're separated by a negative sign here. So terms are separated by negative and positive signs. So you could see both have sine x, and so that's what I took out. That's what we factor out. And when we're factoring out, it's like we are dividing. So if I have, so consider this kind of like my scratch work. If I have sine x, cosine square x, and I factor sine x, of course this 2 will cancel, giving me a 1, and what I have left is cosine square x, which is what I have here. Okay, now if I take this term, negative sine of x, and I factor out sine x, or divide, it will give me a negative 1, and that's what I have right here. So that's how I got those 2. Okay, now the next step is going to be to factor out a negative 1. And why do we want to do that? Well, because we want the expression from here, from the Pythagorean identity, to be identical to the one we have here. And so that is a trick that we use. We factor out a negative 1. So negative 1. This one we will leave it the same. Negative 1 factor out from the stuff that we have here in parentheses. And that will give us negative cosine square x plus 1, or we could just switch the order and write the 1 first. So it will be 1 minus cosine square x. Now, because it does look identical to the one we have up here, so this one is going to get replaced with sine square x. So we have from left to right sine x, the negative 1 is still there, and then we replace that one with sine square x because it's identical to the Pythagorean identity variation. So now all we got to do is multiply. And so we have sine to the first power, sine to the second power. So if we multiply those two, we're going to have sine to the third power. And we cannot forget x. And now the negative 1, we just put it as a negative sign in front of the expression. Example 7, rewriting a trigonometric expression. In this, for this example, we are going to rewrite the expression. Remember, it's only an expression because we don't have the equal sign yet. So that is not in fractional form. So we don't want to have it as a fraction. So what we are going to do, and you will see how we always, not always, but a lot of times we refer back to the Pythagorean identity. So here we have the Pythagorean identity, sine square of x plus cosine square of x is equal to 1. And so what I'm going to do is solve for cosine square x. And so that means I want to leave this one by itself. Cosine square x will equal to 1 minus sine square of x. And that is what we have here, 1 minus sine square of x. Now, why do we want to do that? Well, because 1 minus sine square x is actually a difference of squares. Why? Because 1 is a perfect square, meaning that you could take the square root of 1 and get a 1. And sine square of x is also a perfect square because if you take the square root, you will just get sine x. So, difference of perfect squares, I want to remind you of this little theorem. Let me write it here. If we have a square minus b square, those two could be factored as the product of a plus b and a minus b. And so that is what we're going to do with this one. So this will be factored, and you could see the two factors here. So what we do is we take the square root of 1, the square root of sine x squared. You could see them here, sine x, 1, 1. And the key is to keep in your binomials a positive and a negative sign. So negative, positive. It doesn't matter the order. And so that's how we factor a difference of squares, which is that one. Now, why do we do that? Well, we did that just to demonstrate why we are choosing to multiply by 1 minus sine x. So we start with the question, which is here. Rewrite that fraction, which is here. I just, well, actually, I didn't write it. I just copy pasted it. Rewrite it so it doesn't have a function. So what do? We multiply by kind of like the, when you had complex numbers, the complex conjugate of a number, we used to do that to get imaginary numbers out of the denominator. And so the key with those was to multiply, but the complex conjugate was the same terms, but then the sign in the middle was the opposite. That's how we did complex conjugates. And so this is kind of similar to it, because if you notice here, the fraction has a plus, so we're using the expression that contains the minus, and it all comes from the idea of this. We just did that to show you. Now this is the actual process to rewrite it so it's not in fractional form. So when we multiply something like this, we're going to have 1 multiplied by this expression, so it would just be the same, 1 minus sine of x. That's it. Now, if we multiply this 2, I'm going to do that here on the side. So 1 plus sine x times 1 minus sine x. Okay, so if we multiply 1 times 1, we will get a 1. Now, 1 times negative sine x, or negative sine x. And then we multiply sine x times 1. So that will give me positive sine x. And then positive sine x times negative sine x will give me a negative sine square x. Now, you can see that the two terms in the middle, they are reciprocals, opposites, because they have a positive and a negative sign, so they equal to 0 when we add them. And now we are left with 1 minus sine square x. This one from here, and the negative sine square x here. And so that is what goes here on the bottom from multiplying this term with this term. So 1 minus sine square x. Now, going back to our Pythagorean identity, from the beginning, when we started working with this slide, we noticed that, or we solved for cosine square x, and we got, actually, I'm going to rewrite it because I have so much stuff written on it. We got 1 minus sine square x. So now what I'm going to do is I'm going to replace 1 minus sine square x with cosine square x. Why? Because I am saying they're the same thing. So this will be 1 minus sine x over cosine square x. So remember, we replace this stuff in purple with the other stuff in purple because they are the same. So we're almost there. We're not going to have a fraction. So what I'm going to do next is to separate the fraction and or split the fraction. So that will be 1 divided by cosine square x, because the denominator that I have here is dividing both the 1 and the negative sign. So minus sine square, that is not square, it's just sine x divided by cosine square x. Okay. Now we're going to use the reciprocal identity, but before that, we're going to rewrite the second fraction, this one, a little bit different. And so what I'm going to do is rewrite cosine square as the product of cosine x times cosine x. I'm going to do that next. So 1 over cosine square x. That one I'm just leaving it the same. The next one will be sine x over cosine x times cosine x. That is the same as cosine square x. So why do I do that? Well, because I want to be able to cancel something, or not to cancel, but to be able to use identities. So I'm going to rewrite it again so it makes more sense visually. So we're going to have 1 over cosine square x. I think you all know what that's going to be if we use the reciprocal identity. And then here, this fraction here, I can actually write it as the product of two fractions. So it will be that one times something divided by cosine x. And what will that something be? A 1. Now we could use reciprocal identities for all. So the reciprocal of 1 over cosine square of x will be secant square of x. The reciprocal of, by the quotient identity, sine x divided by cosine x is tangent x. And then 1 over cosine x is the reciprocal of secant x. So that is our answer. We have all of them here: secant square, tangent x, and then we have secant x right there. And so there we have it. We rewrote the expression so that it didn't have any fractions.